Yeah, good morning. Today we are going to discuss about airfoil and geometry selection. So airfoil and geometry selection. Yesterday when we were discussing about airfoil, you know that it is a structural and functional unit. So whenever we are learning about when you are selecting the airfoil, it tells that what type of aircraft you are going to design. Means airfoil plays a very important role in the aircraft design. So we have to take into consideration. So therefore, in this, what we are going to learn is selecting the airfoil wing and tail geometries. Selecting the airfoil wing and tail geometries. We look here, the early airfoils, how they are looking, and we can see the laminar flow airfoil. Mainly, it is a symmetric airfoil. Already yesterday, when I'm discussing, I told you that what is the symmetric airfoil? It is zero camber. The zero camber, for example, NACA 0012. This is such type of airfoils are called as a subsonic airfoils, and we have a later airfoil, circular arc. We can see there will be a circular arc on the upper and the lower surface. Such type of airfoil are called as a circular arc airfoils, and a Clark Y airfoil, it is subsonic, and we have a double wedge airfoil, they're called as supersonic aircrafts. Mainly supersonic aircrafts we are going to look. So such type of airfoils, and when you look here, uh, vertical tail and we have a wing. We have both the type of when you look into a small wings, we'll call tails are called as a small wings. In this tails, we are going to use mostly the most of the times we'll use only subsonic, that is called symmetric airfoils. Mainly we'll use symmetric airfoils. Why? Because symmetric airfoils at a zero angle of attack, there will be no lift. So due to that, we are using the in the vertical tail and horizontal tail, mainly symmetric airfoils we are going to use it, because they act as a stabilizers, horizontal stabilizer as well as vertical stabilizer. We can see that there are different configuration of tails I will discuss in the later stages. So you look here in the wing. So wing cross section of the wing, it looks as a cross section of the wing when you look. So there is an airfoil. You can look the airfoil shape. When you cut the wing, you can see the airfoil shape. Means the series of airfoils will be there. The skeleton of the wing, it is made up of airfoils. And you can see this is called leading edge, and this is as a plane perpendicular to wing, and this is a V infinity is called free stream velocity. We'll call V infinity is nothing but a what? Free stream velocity. And so this is the thing, and we have a trailing edge, leading edge of the airfoil and trailing edge of the airfoil, and we have a plane perpendicular to the wing. And when you when you are cut into to the cross section of this, it looks, you can see that there will be a airfoil. And you can see here low speed airfoils, airliners, propeller blades. You can see most of the propeller blades, it will be look in this such type of airfoils. You can see the 15 centimeter will be the thickness, and 1 meter, and we have supersonic interceptors, and we have a turbofan blade. You see the turbofan engines, we can see that the compressor blades and the turbine blades should look like this. You can see that. And also in a wind tunnels, also when you look at the compressors and turbines, it looks, that is the shape of the airfoil will be, it looks like this. You can see that 80 centimeter of thickness, and also you have blackbird and around 6 centimeter, and dragonfly wing. There are the different types of airfoils. You can see here in the aircraft, helicopter, the rotor blades also will have a airfoil shape. And also when you look here, Zeppelin, UAV, space shuttle, and the parachutes, you can see the parachute also have a shape of the, you can see the shape of the airfoil, because that gives the, that is streamlined, that gives a smooth flow, and also it gives the lift. So already you know that what happens in there is a pressure difference between the upper and lower surface, which makes the body to lift. That is the same phenomena. It will be applicable for all the type of devices in the shape of an airfoil. You can see that it looks like a airfoil. And also we can see the rockets, and we can see here, this is called rotation of the wind turbines, the wind flow across it. You can see here. So when it rotates, so by that you can see airfoil shape. So how it moves, there will be a drag, and it will be a laminar flow over it, and there is no flow separation, and it will give a necessary lift. Okay. So in the race cars also, it looks like a, it will be like a shape of streamlined body, like an airfoil. And so when you look into engines, the gas turbine engines it may be, and we have a propeller based aircraft, you can see that there's the blades, it's the shape of a airfoil. You can see that shape of the engine. It is in the shape of an airfoil. And also when you look at a ship, we can the ships also we can look as a, they're the body of the ship. You can see that it looks like a streamline. You can see it looks like airfoil, and they have a streamlined body. They're called as a streamlined body. And you can see that they're the propellers of it, and we can see that fans the ship propulsion technologies. So there also we use the not of them airfoil shape. And also you can see the shape of this. It looks like a airfoil. You can see here in the the most of the ships in the oceans, when they are traveling, we'll be having a time with like uh, airfoil shape. So here the wind, when it blows with the higher velocity, when the wind comes and hits to it, it should not break into two pieces, correct? There should be a smooth flow over the surface. So therefore, to have a smooth flow, taken this type of shape that is called airfoil shape. We can look here, that's called an airfoil shape. And also we can see that the wind goes very smoothly and it can transforms here, and there will be no much disturbances for the motion of the ship. Clear? So therefore, so it's the most important parameter, that is airfoil selection. So in the aircraft design, so airfoil selection, by selecting the airfoil, it affects on the cruise speed. It means that the aircraft for supersonic, subsonic aircraft we have, means by selecting the airfoil, we can tell that we are going to design supersonic aircraft, or it may be a subsonic aircraft, or what purpose of the aircraft will be determined by selecting the airfoil. And takeoff and landing distances also will be determined by the airfoil selection, because most of the, that is the cross section of the wing is made up of airfoils, that is the lifting surface, correct? And stall speed, you know that what is the stall? Stall is nothing but a what? Whenever the, when you change the angle of attack of the airfoil, at a certain angle of attack, there will be a lift will be minimum and drag will be higher. At that time, at a higher angle of attack, lift will be less, drag will be more. It leads to the aircraft to stall. That is called stall speed, we will call it, is called stall speed. And handling qualities, the aircraft handling qualities, that is the pilot experiences these handling qualities, smooth or not. So how the pilot feels, handling and flying qualities we will call, that is especially near the stall. How is the feel of the pilot, that is called near the stall. These are called handling qualities, also is dependent upon the airfoil selection. And overall aerodynamic efficiency during the phases of flight. So all the overall aerodynamic efficiency, that is L by D, we can determine lift to drag ratio. It is called, it determines the aerodynamic efficiency during all phases of flight. And we can see here, this is called landing distance, and V stall, that is called stall velocity. It depends upon the wing loading, and I will discuss in the further classes about it in detail. And you can see that airfoil geometry. So this is called round leading edge. You can see this is called round leading edge, and we have angle of attack. There will be a thickness from the upper surface to the lower surface. That distance is called thickness. And we have it, this is a camber, and this is the upper surface and lower surface. This is called a chord line. And understood, this is a camber thickness. This is cambered airfoils and symmetric airfoils. There will be zero camber in the, there will not be a camber in the symmetric airfoils. We can cut that airfoil into two pieces equally. Understood? But in the cambered airfoil, what happens? We can see the camber, and we can see that there will be a sharp edge at the trailing edge. Yeah. So total airfoil. So we can look here, and the total airfoil camber is defined as a maximum distance of the mere camber line from the chord line, expressed as a percent of chord. And also this is called airfoil thickness ratio, we will call T by C. That is called airfoil thickness ratio. It refers to the maximum thickness of the airfoil divided by its chord. That is called T by C, we will call. And we can have a airfoil lift and drag. And airfoil generates the lift by changing the velocity of air passing over and under itself. You can see that there is an airfoil, the flow will be over the airfoil, and there will be faster the airflow, and it will be slower the air, and there will be high pressure. Yesterday when discussing, I told that it is a high pressure and a low velocity, and there will be a low pressure, high velocity. So you can see that how the distribution of the pressure, you can see that the pressure and the velocity of it, lower surface, and this is the upper surface, and this is called center of pressure, which makes the body to lift. Understood? There is a lift and a drag, and there will be a resultant force which makes the body to lift. Correct? So therefore we can see here and we can see this is called and we can see this is called CL versus alpha curve. This is called CL versus alpha curve, and we can see this is called center of pressure. Center of pressure, it is a pressure coefficient, and this is called a lift coefficient, C small l. And also one thing we have to take into consideration, C suffix small l, it is called coefficient of lift of the airfoil. Means C small l or small l, when you are representing, I am speaking about a airfoil. If I'm speaking about a capital L, that is C capital L, it is called what? C capital L is called, I'm speaking about a 3D, that is about the wing. And the integrated differences in pressure between top and bottom of the airfoil generates the net lifting force. Already you know that the pressure difference between the upper and the lower surface, it leads to the lift. Note that upper surface of the wing contributes about 2/3 of the total lift, that is 2/3 of the total lift. And we can see here the pressure coefficient, and we can see upper surface how there will be a negative pressure, and we can see the positive pressure at the lower surface. It means that the lower pressure have a high pressure and the upper surface have a low pressure, and it contributes to 2/3 of it. And we can see about it completely about lower surface, so therefore there will be a pressure difference between the upper and the lower surface. It leads to the lift. Therefore, Cp is given by P minus P infinity, that is called free stream pressure, and it is called a free stream density. It is a free stream velocity. Always infinity, it represents what? Free stream. It represents free stream. And we can see here, and when you look here, this is called total aerodynamic force, sum of the pressure and shear forces. And when you look here, lift, drag, and moment coefficient. See, small l, I told you, small l represents, you can see that is C small l. It is, I'm speaking about airfoil. If it is having a C capital L, this is called, I'm speaking about wing, that is 3D. And C small l, I'm speaking about a 2D. So therefore, lift, drag, and moment coefficient. Lift, drag, moment of an airfoil. L is nothing but for lift per unit span. D is nothing but for drag per unit span. M is moment per unit span. So already we know that alpha is angle of attack. V infinity is free stream velocity. And rho infinity is free stream density. And we can see here, when you look here, so CL is nothing but a what? L by half rho V square. This infinity, it represents what? It represents free stream density and free stream velocity. And we can see it alpha, RE, and M infinity. It means that alpha is nothing but an angle of attack. RE is nothing but a Reynolds number. Reynolds number is nothing but a what? Rho VD by mu. Understood? The inertial to the viscous force. That's a Reynolds number. Means Reynolds number determines that what? The flow is turbulent or it may be a laminar. According to that, we are determining the flow. That is Reynolds number. And M infinity is nothing but a Mach number. It is free stream Mach number. What is this Mach number? Mach number is nothing but a what? It is speed of an object to the speed of a sound. That is called as a Mach number. So lift, CL, it is the function of angle of attack, Reynolds number, and free stream Mach number. And also we can see CD, C suffix D, small d, that is D by half rho V square infinity C. It is same as that of the coefficient of lift and coefficient of drag. All small suffix, you can see that these are all the subscripts what we are using. Small l, small d, it all represents for the 2D, that is for only for the airfoils. If they are capital L, capital D, it is for wing. Okay, it's a function of alpha, RE, Reynolds number, and free stream Mach number. So we can look here. Alpha is angle of attack, V infinity is free stream velocity, rho infinity is free stream density, and C is airfoil chord length. This is called C is nothing but a what? Airfoil chord length. And what is the length of the chord length? You can see that the first here to, that is leading edge to trailing edge, that is the length, that is called C. Understood? It's a chord length. That M infinity is free stream viscosity. And when you look here, so and you can see here A infinity is called free stream sonic speed, and we have a, you can see a subsonic, sonic, that is called transonic, and we have a supersonic. We have 3 stages when you look here. Subsonic is less than 0.8, and we can see that there is a transition stage of it. It is sonic around 1, and Mach and 1.2. Once it crosses 1.2 Mach number, then it is called as a supersonic. It is called as supersonic. And Q infinity is called free stream dynamic pressure. It is called what? Free stream dynamic pressure. It is called free stream dynamic pressure. And free stream dynamic pressure. And when you look here, this is called section of the lift coefficient, the characteristic of NACA 1412. See, we have to understand here, I will discuss in detail about this. What it is, nothing but a 1412. Last two numbers represents thickness to chord ratio, that is T by C, the thickness of the airfoil. This 14%, what it is there, it is a chord distance. So therefore, we have to take into consideration this NACA 1412 is nothing but this is a symmetric airfoil. If in the first two numbers are 0, then it is called symmetric airfoil. If it is NACA 14, this is a number, what it is, that is called cambered airfoil. If it is not 0, then it is called a camber thickness, we'll call that is 14% of it. Here, so we will discuss in detail about it. And we can see here, this is called cambered airfoil and symmetric airfoil. Now we can discuss here. See here, cambered airfoil, we can see here there is a, and there is having a camber line, and there is no camber here. It is called 0 camber, and this is having a camber and camber thickness. When you look into a in the airfoil nomenclature, you will understand clearly that is CL versus alpha. In this CL versus alpha, we can see here at a 0 angle of attack, we can see it's a negative. It is 0, -1, -2. We can see 0, +1, +2, like this when you take a graph. So in the negative, the value also we can see the left. But here what is happening at a 0-degree angle of attack also, we don't have any left, correct? So therefore, symmetric airfoil at 0 degrees CL versus alpha will be, when you look into it, lift will be 0 at a 0 angle of attack, but in the negative angle of attack also we can see the lift in the cambered airfoil. Most of the cambered airfoil will be used, understood, so in the wings itself. In the symmetric airfoils will be used in the tail sections, that will be vertical as well as horizontal stabilizers, horizontal tail, that's and where we fix elevators as well as rudders is a vertical tail as well as horizontal tail. Clear? And we see a tail with respect to the horizontal plane. So at 0 degree. See here in the 0 degree, the angle of attack is 0 degree. You can see that there is a flow separation is less here. So in the 5 degree, you can see it is shifted now. This point is shifted just a little ahead. We can see here, and this again in the 16 degree, the stall angle again is shifted in the very early stage. Means in the early stage, there will be a flow separation. Means it leads to a stall angle. Means at a higher angle of attack, there will be maximum lift will be there. Once it crosses, what happens? Lift drops and drag will be higher, then it loses its control. So you can see at a 20 degree, separation of flow region expands and reduces lift. That is called large turbulent wake reduced and a pressure drag. We can see that very early stage itself, we can see the flow separation, that is called separated flow region expands, the reduces the lift, that is called turbulent wake, reduced lift and a large pressure drag. Clear? These are all called L by D max and CL max and CD and L by D. Clear? And you can see CL versus CD. CL versus CD. This is a very important, please understand here. This is called drag bucket. It is nothing but a drag bucket is nothing but a what? A low drag region. It means that pilot, when he is flying in this region, there will be performance of the aircraft will be good. It means that drag will be less and the performance will be good, lift will be good, and we can fly very smoothly. This is called laminar bucket. It's called conventional airfoil polar, we'll call it. It's called low drag region. In this, when we are flying in this region, what happens? There will be a drag will be less and the performance of the aircraft will be good. So therefore, drag bucket plays a very important role. What is this drag bucket? It is nothing but a what? It is nothing but a low drag region. Drag bucket is nothing but a what? It is a low drag region. And also we can see CL max and alpha stall. The stall angle is nothing but a what? There is an angle. It is an angle where the maximum lift will be produced. Beyond that angle, there will be a what happens? That is adverse effect on the lift, and lift reduces and drag will be higher and turbulency will be, wake formation will be there. So that one we have to understand. And we can see our airfoil families. Early airfoils were developed mostly by trial and error. And this year you have to give your attention. Look here, you have a Wright 1908, Blériot, and RAF 6 1912. These are the Göttingen, Clark Y, M6, and RAF 34. And NACA 2412, NACA 23012. These are all the different type of airfoils when you look into it. In 1930, NACA and this is the council, National Aeronautics of Council. The members of this, in America, what happened here, developed a widely used family of mathematically defined airfoils called 4-digit. This is NACA is the thing, but a NASA. That before they was called as a understood the Constituent Assembly, that is like a aeronautical assembly. Now we are calling it as NASA. Understood. Used family of mathematically defined airfoils called the 4-digit airfoils. It's called what? 4-digit airfoils. And while rarely used for wing design today, that is uncambered 4-digit airfoils are still commonly used for tail surfaces and subsonic aircrafts. And NACA 5-digit were developed to allow the shifting the position of the maximum cambered forward for greater maximum lift. And 6 series airfoil, and we have a design for an increased laminar flow and reduced drag. And 6 series airfoils such that 64A series we will call are still widely used as a starting point for high speed wing design, and like a F-15 aircrafts mainly we are using 6 series aircraft, 6 series airfoils that are 64A. These two shapes of low drag sections designed to have a laminar flow that is 60 to 70% of the chord on both the upper and the lower surface. So 60 to around the lower and upper surface will be chord will be 60 to 70%. So therefore we have to understand what all things are there. We have a 4 series, we have a 5-digit, and we have a 6 series and 64A series. Clear? So this airfoil design, in the past, the designer would select an airfoil from such a catalog by considering airfoil drag during the cruise. How we are going to design this airfoil? So in the previously, the designer used to do what he used to do. So during the cruise, how much this airfoil is experiencing a drag. According to that trial and error, we are going to check, okay, fine, this type of airfoils, if you use, it will be good for my design. That is called airfoil design. Stall and pitching moment characteristics. Stall and pitching moment. What is the stall? Already you know that it is an angle where the maximum lift will be there, and once it crosses, there will be a turbulence will be high, wake formation will be there, and it loses its control. Correct? And pitching moment characteristics and the thickness available for structure, because thickness available for a structure and a fuel and the ease of manufacture. You understand here, thickness available for structure, what it means? It means that, so thickness in the wing, we can see that the fuel, the home for the fuel is wing, correct? So therefore it tells that how much fuel you are going to store, that much of the range of the aircraft will be there, correct? So therefore the thickness available for structure is determined by the airfoil. What should be the thickness of the airfoil, what should be the space of the airfoil, it all will be depend upon the airfoil design. With today's computational airfoil design capabilities, we have a CFD analysis today. So by that we can tell that what should be the thickness, what should be the understood thickness to chord ratio, all things we can analyze by the flow analysis. It is becoming common for the airfoil shapes for a wing to custom design, and you can see the methods have been developed for designing the airfoil such that we have the pressure differential between the top and bottom of the airfoil quickly reaches the maximum value attainable without flow separation. And towards the rear of the airfoil, various pressure recovery schemes are employed to prevent the separation near the trailing edge. So what is this quickly reaches the maximum value? Is a pressure differences between the top and bottom. This pressure difference between the top and bottom leads to the lift, correct? So therefore, when it reaches to the maximum value without flow separation, if the delay in a flow separation, there will be a good lift. If separation occurs with an early stage, and we can see that, and when it is flow separation occurs in the early stage, the drag will be higher, wake formation will be there, vortices formation will be there. So to delay that flow separation, our goal will be there. So therefore we have to understand in the airfoil design. So therefore airfoils with a substantial pressure differentials over a much percent of chord than the classical airfoil, and this permits a reduced wing area for a required amount of lift. And also we can see a round leading edge. So in the airfoil, in the previously I shown you the figure, their round leading edge, you can see at the leading edge you can have a circular shape, that is called round leading edge, that is called increases pressure quickly. And you can see a gradual tapering of the shape of a trailing edge reduces likelihood of separation under the adverse pressure gradient and camber. This curvature determines that how much lift generated at zero angle of attack. So when I seen at a cambered airfoil, we can see that there will be a sharp at the trailing edge. That is called at a zero angle of attack. At a zero angle of attack, how much lift is generated? We know that cambered airfoils in the negative angle also we can get the lift. So therefore we are interested to know that at 0 degree what the lift will be generated. Clear? And most airfoils are designed using the uh, codes based on the potential flow theory. Please understand what is this potential flow theory. You know that what is potential? Potential is nothing but a hidden energy, or it may be virtue of its position. Means how much the energy, how much the pressure, how much the flow under the below the surface as well as above the surface, which leads to the aircraft to lift. So therefore that pressure difference, that will be according to that how much potential flow theory, how much energy in between the pressure between the upper and lower surface, that will tell us about the potential flow theory. Please look into it. Just have a note of it, potential flow theory, and just read further. Okay. And with boundary layer corrections, but can one use as a wind tunnel data and inverse design methods. So you can see here, most airfoils are designed for a specific design point. Why we need to design the airfoils? Because specific design point, one is to get a maximum lift and to get a maximum thickness. So if you have a maximum thickness, we can store the fuel much, and also there will be a lot of effects will be there on the performance of the aircraft. And we can see the transonic flight, and we have a laminar boundary layer, we have a low Reynolds number, low pitching moment. So these are all are the parameters which are the design parameters where we are going to look when you are going to design the airfoil. So in layer in the airplane is flying just under the speed of sound, is faster air traveling over the upper surface will reach the supersonic, causing a shock to exist on an upper surface. So what it means that here there is a point when the airfoil, when the flow over the airfoil, when it reaches to a unity, then what happens, that is called critical Mach number we will call. So what is this the shock formation? The shock is nothing but what when the aircraft is moving at a higher speed, what happens, that suddenly it will be drops and it to a subsonic. That is a point that is called shock formation. That is when the aircraft is moving at a faster rate, what happens due to the higher speed, there will be a, when it hits, that will be reduced as a m greater than 1 to m less than 1. Clear? And what is the critical Mach number is nothing but what on the surface it reaches to the in unity, m is equal to 1, on which point where m is equal to 1, that is called critical Mach number we'll call. Means the speed at which supersonic flow first appears is called a critical Mach number, or it reaches to the unity, that is called critical Mach number. That is m infinity is 0.3, that is critical, that is called free stream Mach number, and this is called free stream Mach number 0.5, and m critical is should be greater than 0.61, means it will reach us to the infinity. This is the point where m is equal to 1, means on this point onward there will be a supersonic flow. There will be a supersonic flow. You can see that there is a bubble formation on that, means that is the point where after that there will be a supersonic flow will be there. And we can see these are called supercritical airfoils, and we have a highly cambered airfoils. You can see little camber, it is a highly cambered, and supercritical airfoil is one designed to increase the critical Mach number. So supercritical airfoils are the type of airfoils to increase the critical Mach number. So we are using such type of airfoils. And you can see that there is a Mach number conventional airfoils and supercritical airfoils. We can see Mach number, it is around 0.6, 0.7. You can see that 0.68, 0.69. You can see they're all used, supercritical airfoils are used for mainly in the supersonic. You can see that higher the rate, you can see that coefficient of drag versus Mach number. And it's a conventional airfoils will be maximum will go over 0.8. Understood? It will be beyond it. That is called supercritical airfoil. Why we are using supercritical airfoil? To increase the critical Mach number. Clear? So design lift coefficient. The first consideration of the initial airfoil selection is design lift coefficient. This lift coefficient at which airfoil has best L by D. What is this L by D? Lift to drag ratio. This is the lift coefficient at which airfoil has best L by D. So we can look here, and this is called min drag condition. This is the point where it is a minimum drag. This is called CDMD, is nothing but a min drag, coefficient of drag at the minimum drag. So therefore tan theta, it is coefficient of lift as the min drag and coefficient of drag at the min drag, that is called L by D max. What is this? Nothing but what? Maximum lift, and understood, maximum lift and drag, there will be a maximum minimum drag position at the both the things. So therefore lift and L by D will be maximum. What is this L by D? L by D determines the aerodynamic efficiency of the aircraft, aerodynamic efficiency of the aircraft, that we have to understand. So, and also we look here, and we can, the subsonic flight, and subsonic flight has well designed airfoil operating at a design lift coefficient, and that is lift more than the skin friction drag. The aircraft should be designed so that it flies at the design mission at a near design lift coefficient to maximize the aerodynamic efficiency. This aerodynamic efficiency will be determined by L by D max, L by D max. So we can see that W is equal to L. So yesterday when you were discussing, we discussed about it, steady level unaccelerated flight. That is, when it is steady level unaccelerated flight, what is happening? Lift is equal to weight, thrust is equal to drag. It means that we can say W, it is the weight, and L is the lift. So therefore QS into CL. So this capital L, it is called wing lift coefficient. Small l is nothing but a what? Airfoil lift coefficient. So therefore it is for 2D, and this is for capital L. It is determining for a 3D. It is for wing, as well as this is for small l. It tells about airfoil. Wherever we subscript of small l, it is called airfoil. It is for airfoil, capital L for wing. Okay, so CL is nothing but a what? 1 by Q, and this is called W by S. So we'll discuss about it. This is called wing loading. We will call this is called W by S is nothing but a what? Wing loading. Fine. This Q is nothing but a dynamic pressure, where it is the function of velocity and the altitude. When the, because dynamic pressure, you know that having the higher the altitude, what happens to the pressure? It varies with the altitude. So therefore CL can be calculated for the velocity of the altitude of the design mission. So we can look here during the mission fuel. So W by S, wing loading will reduce us. Why wing loading will reduce us? The fuel consumption will be there. So therefore wing loading will reduce us. To flight with high lift coefficient. Always remember, dynamic pressure decreases with increase in altitude. The pressure decreases with increase in altitude. And we can look here, and we can cruise climb flight and the maximum range. So therefore always just we have to remember that it is the dynamic pressure decreases with increase in altitude, and it's a cruise climb flight with a maximum range. And in actual practice, design lift coefficient usually will be based upon the past experiments. For most types of the aircraft, typically will be around how much it is? 0.5. Please remember, typically we will take with a 0.5 for the design lift coefficient. Understood? So therefore 0.5 will be around design lift coefficient, and that's for the historically what we are going to look. So in fact, initial selection of the airfoil is often simply based upon prior experience or copied from some successful design. So we will check that whenever you are going to design for a particular aircraft. For example, if you're going for anti-submarine warfare, so or it may be Sukhoi, or it may be F-15. So when you are going to design for a particular aircraft, we'll check that. So it's the same type of aircraft I am going to design in my lab. So what I will do it at the time, I will check what type of airfoils they used. According to that, I will check, okay, fine, these are the performance of the aircraft, so therefore I can use same type of airfoil for my aircraft also. That is called competitive studies. We will call that is called competitive studies. So now the concept comes, what is stall? The stall characteristics play an important role in airfoil selection. Already you know that what is stall. So when you increase in the angle of attack, what happens? There is a flow separation occurs. When the flow separation is occurring, what happens? There is a point where we will get a maximum lift. After that lift, what happens? That point when it crosses, there will be a drag will be higher compared to the lift. So therefore, so at that time it loses its control. That is called stall angle, we will call. So it plays a very important role, and that is mainly the handling qualities of the the pilot. For handling quality for the pilot will be seen in the stall area. Okay, some airfoils exhibit a gradual reduction in lift during a stall, whereas others show a violent loss of lift accompanied by a rapid change in pitching moment. This difference reflects the existence of three entirely different type of airfoil stall. You can see here we have a different type of three airfoils. We can see here these are the different type of airfoils according to the angle of attack. We can look into it, that the wind tunnel. So we can, this is called as flow visualization techniques, we will call. So what is this flow visualization technique? Mainly for subsonic, we'll we'll go for in a wind tunnel, smoke flow visualization technique we'll do. What we'll do, we'll put a smoke. By that, what happens, we can see that where the flow separation is occurring. In the wind tunnel, we'll test. That is called the flow visualization techniques, we will call. The flow over the airfoil, to check that, the techniques called flow visualization techniques. And we have a different type of airfoils, that is fat airfoil. So it will be segregated on the basis of T by C. That is called thickness to chord ratio. If it is greater than 14%, then it is called fat airfoil. If it is in between 6% to 14%, then it is called thinner airfoils. Then it is called thinner airfoils. And we can see that, just go look into this, and very thin airfoils is less than 6%. Understood? So therefore, we have to understand the different type of airfoils on the basis of T by C. Just look into it further, you study on that and you'll understand. Okay, so here NACA 4412 versus NACA 4421. See, look here, this is last two numbers. What is that here? 1 2 and 2 1. This is 1 2 is nothing but a what? 12%. It is nothing but a thickness to chord ratio, T by C, and 21% of the thickness. Okay, so what is happening here? So this is the that is section where the CL versus understood. When you look here, understood. When you look here, CL versus alpha curve. This is CL versus alpha NACA 4412. That is 21% of the thickness, and this is a 12% of the thickness. We can see which is having a highest CL here. It is having a NACA 4412, correct? So therefore, when you see a NACA, if the thickness is increasing, it affects on the CL, it affects on the section of the lift coefficient. So therefore, higher the thickness will be the lesser the CL. And we can see that we have a leading edge stall. We can see, and also we can see that we can have a sustainability will be higher when it is in the higher thickness. We can see it will goes and it will drops at a early stage. So therefore, what it says here, look here. So therefore, here the loss of lift is gradually on the pitching moment changes only in the small amount. Means the 14%, greater than the 14%, what happens? Well, now we'll segregate it. If 21%, what type of airfoil is it? It is greater than 14%, that is fat airfoils. Fat airfoil. NACA 4421, it is called fat airfoil. What is the characteristics of this is? That is alpha, that is turbulent boundary layer at 10-degree boundary layer begins to separate starting at the trailing edge, increase in the angle of attack. Moving forward, the loss of lift is gradual. The pitching moment changes only a small amount. But when you speak about 12, NACA 4412, that is, it is a thinner airfoils, it will come. We can see the flow fails to reattach, entire stall. So therefore, when you look here, it is reattachment of the flow will be there. So therefore, it will fall. It will fall at once it go to the higher and it will fall. Understood? But it will not happens here. It will take some time to fall down. Clear? That is the effect of thickness. That is 21% as well as 12%. Clear? So therefore, thin airfoils theory predict that linear slope of alpha L is equal to 0 should be the same for both. And the leading edge stall shows the rapid drop and lift curve near the maximum lift. And trailing edge stall shows the gradual bending over the lift. So therefore, leading edge stall shows the rapid drop of a lift curve near the maximum lift, and trailing edge stall shows the gradual bending over the lift curve at maximum lift. That is called soft stall. We'll call it. It's called soft stall. And high CL max for airfoils with a leading edge stall and flat plate stall exhibits the poorest behavior early stalling. And thickness plays a very important role on the CL max. Please make the note of it here. Thickness as major effect. So therefore, you can see that thickness as major effect. We can see here a thin airfoils and you have a flat plate, and with thickness CL max plays a very important role. Understood? So what happens here? And also we'll induce a wing twist is introduced to prevent the stall. So this stall is a very important parameter. So to avoid that stall, what we will do, we will induce a twist angle that is called the wing twist. The twist angle is introduced to prevent the stall from occurring at the wing tip before than the wing root. Usually the wings are washout twisted, resulting in decreasing the angle of attack. Start from the towards the tip, and washout twisted and washing twisted. I will discuss about it clearly. Just look here. Precisely the twist angle is the angle between the zero lift line of the profile and the current. We can see here in this washout twist and washing twist. We can look here. And the precise twist angle is angle between zero lift line of the profile and the current section of the zero lift line of the root profile. As the twist angle increases along the span, and the lower is the local angle of attack and the lower is the lift generated. By this, we prevent the wing tip from generating as much as lift and the wing root. So therefore, wing root is nothing but a what? It is towards the fuselage is called as a wing root, and wing tip is towards that. It is called a wing tip, we'll call. So therefore, there is a twist will be induced to reduce the stall. Why? How we are going to reduce the stall? By inducing the twist angle. By washout twist, we obtain to make stall occur at the wing root without loss of ailerons. So what happens if stall occurs on the ailerons? It loses its control. To avoid that, the stall occurring on the ailerons, so to what we will do, we will introduce the twist called washout twist. We will introduce the washout twist, and this is called, you can see here, this is called wing root and this is called a wing tip. So when the stall is occurring, what happens if it occurs on the ailerons? There will be adverse effect will be there. It loses its control. So therefore, to avoid the stall occurring on the ailerons, so what we will do, we will induce the twist. By inducing the twist, what happens? Twist angle, we will avoid the stall occurring on the ailerons. Clear? So therefore, this provides a good flow over the ailerons, roll control at angle of attack where root is stalled. So we can see NACA 643218, and we have a quick stall, gradual stall. It is always lift coefficient versus alpha, CL versus alpha. So we can see here we have a root, and this is called a mid span, and this is called a tip span. This is a span of the root, tip, and a mid span. You can see NACA 00. See, this 00 is nothing but they are called as symmetric airfoils. NACA 634 and 221 is called as a 63-bit series of the NACA. They are the different series of the airfoils. Okay, so now we are speaking about airfoil thickness ratio. The airfoil thickness ratio has a direct effect on drag. If the thickness is more, drag will be higher, because you know that if the larger that, the drag will be higher, and maximum lift and stall characteristics and structural weight. If thickness is more, it increases the structural weight. Correct? So therefore, we can see here. So we will look here. T by C is increasing, drag is increasing, and critical Mach number is decreasing. What is this critical Mach number? That is a Mach where it is reaches to the unity, the flow over the airfoil. It reaches to the infinity, where it reaches where it will be supersonic at that point. That is called critical Mach number. It is called, and also you can see capital lambda is called 47 degree. It is called sweep angle. We will call it. It is called what? Sweep angle. So therefore, minimum wing drag coefficient CD minimum versus Mach number. It depends upon the T by C. If a T by C is increasing, CD also increasing. So therefore, supercritical airfoils designed to delay and reduce the transonic drag rise due to both strong normal shock and shock induced boundary layer separation. So therefore, relative to conventional supercritical airfoil, as reduced amount of camber increase the leading edge radius, small surface curvature, suction side, concavity is rare part of the pressure side. You can see this is called concavity. What is concavity? Cave. It is at a curved portion. Understood? So therefore, we can see that this is called a strong shock and separated boundary layer. And we can see this is a shock where it is M is greater than 1, and there is a separated boundary layer, and it is M is greater than 1. We can see that M is greater than 1. We can see that's a concavity at the bottom, and we can see a concavity at the upper. That is the thing what we are suction side, we'll call it. It's called a suction or concavity in a rare part of the pressure side. And this is of the aircraft, and optimum airfoil thickness. And the thickness ratio affects on the maximum lift and stall characteristics primarily by its effect on the nose shape. And it depends upon the nose shape. You can see that F3 Alpine, we have a nose shape, the nose of the aircraft. It depends upon the nose of the aircraft. I will discuss in detail about it. And just look here. A large nose radius provides a higher stall angle. See, if the nose radius is sharp, it will be a lesser stall angle. If large radius is, radius is larger, than the higher stall angle. Greater maximum lift coefficient. So with the high aspect ratio, we will call that moderate sweep. Vice versa with the low for low aspect ratio. We have to understand what is this aspect ratio. Square of the wingspan divided by surface area. Okay. The NACA 63 and 63212 last number, it represents what? Thickness. It is optimum selection of it. So we can look here and see a structural weight is 1 by square root of the T by C. Always structural weight is depends upon, it is inverse of that square root of the T by C. halving the thickness ratio, wing weight increases by 41%, and wing weight is typically about 15% of the empty weight, and halving the thickness ratio is empty weight increases by 6%. So therefore supercritical airfoils would tend to be about 10% thicker than the historical trend. We have to go accordingly, and we can look here, and when you look here, so due to the fuselage effects, the root airfoil is subsonic aircraft can be much as 20 to 60% thicker than the tip airfoil without greatly affecting the drag. That is a very beneficial, resulting in structural weight reduction as well as more volume fuel in landing gear. So therefore we have to give a where the according to the thickness of the airfoil, it determines that the how much the fuel can be filled, and also it gives the structure for the landing gear, home for the landing gear. This thicker root airfoil should extend no more about 30% of the span. And other airfoil considerations are, another important aspect of airfoil selection is Reynolds number. Already you know that Reynolds number. So it's a function of Reynolds number, free stream Mach number, and angle of attack, correct? So therefore each airfoil is designed for a certain Mach number. So that is a Reynolds number, for example, is greater than 2000, less than 2000 for laminar. If it is greater than 2000, it is for turbulence. So therefore Reynolds number plays a very important role in designing the airfoil. Understood? So therefore this is the important for laminar flow airfoils, and most crucial when an airfoil is operated at a lower than design Reynolds number. So we can just look here. So an aircraft designer should not spend too much time during pick exactly the right airfoil in early conceptual design. Conceptual only just spending the whole life in the selecting the airfoil, it doesn't make sense. So therefore by competitive studies we have to get a right ballpark. Okay, so therefore later trade studies and analytical design tools will determine the desired airfoil characteristics and geometry. So for early conceptual layout, the selected airfoil is important, mostly determining the thickness. So always remember, the first we are going to look the parameter called thickness available for structure, landing gear, and fuel. If the thickness is larger, so we can give the fuel can be filled, as well as we can give the home for the landing gear in the wings, correct? For swept wing supersonic, NACA 64A and 65A sections are good airfoils for the initial design. So therefore for swept wing supersonic aircraft, NACA 64A, 65A, please, these are the series of the airfoils which are good airfoils for the initial design. So this is about airfoil selection and the wing geometry. So we have to understand how the airfoil is affected on that, and what are the parameters. You can see here when I'm telling up, so you can see that it's a nose shape of it, and you can see the nose shape. These are called a supercritical airfoil. You can say it depends upon the what type of airfoil I used. According to that, it depends upon the speed of the aircraft. If it is the larger the nose radius, there will be a, so what are the larger the nose radius, what happens here? If it is larger, the nose radius provides a higher stall angle and greater maximum lift coefficient. If lesser that, it is the lesser the stall angle and lesser the maximum lift coefficient. It is a minimum lift coefficient will be there. So it depends upon the it is an airfoil, which airfoil we are going to use. So therefore you need to know all this, and also we can see that conventional airfoil flow separation is CL versus alpha. Look here, this is what is happening in the center of pressure, and it is going and dropping conventional airfoil. But what is happening in supercritical airfoil? It is sustaining. You can see that it is a speed will be sustained for in the supersonic itself. It will take a longer time to reduce it to be a stall, correct? So therefore, so this is the one of the important aspect of supercritical airfoil, the importance of the supercritical airfoil, why we are using in the supersonic flows. Understood? This is called conventional versus supercritical airfoil. You can see how the supercritical airfoil looks. Yeah. So therefore, and we have, and so these are all the effect of the how the airfoil selection plays a very important role in the aircraft design. So please, we have to be lastly we consider that TYC plays a very important role, thickness, because landing gear and the fuel. So the structure of the airfoil thickness depends upon the thickness, and these are all of the things what we have to keep in mind when you are going to select the airfoil. Okay, so if you have any doubts, and